today I have the great pleasure to welcome Momchil Minkov. Momchil was did his studies first in Germany and bachelor studies, and then the master at EPFL, and his career accident to do the master project and PhD with me. But he saved the day by finishing his PhD with 13 peer-reviewed papers. Okay, so and then he went to Stanford to work with Shanhui Fan, who's one of the leading experts in the theory and the simulation of photonic systems. And not only that. And after Stanford, Momchil decided to switch to industry, and he was very brave because he joined a startup at the time, small, who was just starting, but that was because he brought these ideas that have been developed in Stanford about hardware acceleration for simulation of these photonic systems, and now the company is very successful, Flex Compute. I heard around that many people can't, many our colleagues can't live without the software that they sell. And by the way, while always working for Flex Compute, Momchil moved to Switzerland recently, so he's more or less around, not really in Lausanne, but he's around. And today he's going to talk about hardware acceleration and smart simulation of FDTD. For those who have never seen photonics but just quantum, FDTD is a well-established method for simulating the dynamics of Maxwell equations in structured photonic systems. And I'm looking very much forward to listening to your talk, Momchil.
Thank you very much. Thanks for this. But yeah, this is my career path. I was DPFL back when the logo used to look like this. I don't know if I'm allowed to show it. But yeah, I graduated in 2016, and James already explained everything, and I'm really happy to be taking the loop back now here. Even though the logo is different, I'm really happy to be back at DPFL. And okay, so I'm just gonna skip that because it was already explained. And just gonna jump to my outline. So first I'm gonna talk about the hardware accelerated EM solver, which is called Tidy3D. So Flex Compute is the name of the company. Tidy3D is the name of our specific EM solver. There's a completely separate division that does fluid dynamics simulations. And they were even like getting started a little bit before we got started. So it's the same company, but it was co-founded by, so yeah, I guess I didn't mention that. Flex Compute was co-founded by Shanhui, together with two other professors. One of them is Professor of Fluid Dynamics. So it's in general, ambition, let's say, is to be not just an FDTD solver or not even an EM solver company, but more like a complete suite of simulation tools for all sorts of physics. I'm going to talk a little bit about automatic differentiation. That's going to be quite a change of pace there. I'm going to try to give like an introduction to what that really means. Then the agile variable method and inverse design kind of follows more naturally from there, and then I'm going to just talk about something we call inverse design for everybody using Tidy3D. And just to get things out of the way, how much of what I'm going to talk about is going to be quantum, since this is a quantum seminar. So in some sense, unfortunately, not that much, but also everything is quantum adjacent, I guess. So the concepts that I'm going to present, I think, of hardware acceleration and automatic differentiation, I think there will be a lot of kind of take-home messages that might apply to anybody who's interested in simulations in general. Now, I apologize if for people who are very good at those things, some of the things are very simple or look dumbed down too much. But I think for a general audience, there will be some interesting insights. And then, if you're more on the device side, the devices I'm going to be talking about are also not per se quantum, but it's going to be a lot of like, let's say, photonic integrated components, or in general, like light controlling devices. And I mean, if you're doing quantum computing, regardless of what your qubits are, you're probably using light at one point or another, either to control them or to transfer information or something like that. And then, obviously, also there's the whole a bit of quantum computing where photons are actually pure qubits. And a lot of these classical devices are really needed there. And in fact, the requirements for quantum devices are much more stringent than for classical devices, right? Because if you lose a photon in your classical device, you're fine. If you lose a photon in your quantum computer where your photon is your qubit, then you're completely screwed. So the tolerances on things like losses or something like that are even more stringent, and so having a good way to design things that are really highly optimized is like even more important. And you go to flexcompute.com to find a lot of more details about things that I'll be presenting. And for example, and I'll have some links along the way. And for example, we have a blog where we often post kind of success stories from both academic and industry users of guided 3D. And these are some of the, I've just given 2 examples of quantum devices that were studied using guided 3D. And actually we have quite a long-standing, I guess not partnership exactly, but interaction with Xanadu. They've been users of guided 3D for a while, and we finally, so I cannot normally disclose our customers without specific approval from them. So I cannot tell you about all the things that people are doing that are related to quantum stuff or not with guided 3D, but we do have an upcoming success story with Xanadu as well. All right, so then jumping into it. So basically, especially in the last decade or so, parallel computing using GPUs and then even more advanced than that, TPUs or FPGAs has been getting better and better. I mean, NVIDIA is now, I think, the second most valuable company in the world because of what they provide. And what they provide is GPUs, and what they're needed for mostly is data centers for AI. But in general, this has pushed the compute speed of these specialized devices to exponentially. And it turns out that these same advantages that kind of AI has brought, or the way that AI has pushed this hardware to develop, like a lot of these gains can be utilized also to do physical simulations fast. Now, I'm mostly going to focus on GPUs because with TPUs you don't really have access to unless you work with Google, and FPGAs are great if you have enough money to design them for yourself. But in principle, GPUs you can go off the rack and you can do an amazing job at speeding up simulations. One slide on the MTTV method for Maxwell's equation specifically. It's just a way to discretize the electric and magnetic field on a finite Cartesian grid. And each of the field components actually live at a different location on the grid. And that is kind of dictated by how Maxwell's equations work. Specifically, for example, a given electric field component, like the easy here, is related to the magnetic field through the curl. So this is like a natural construction where the electric field here can be updated through the curl of the H field around it. And this is the very, very basic update equation for the time domain, so finite difference time domain algorithm, where essentially so I'm neglecting all sorts of complications like boundary conditions or displaced materials or even a complicated material distribution or something like that. But we're just going to try to elucidate some general principles about what determines the speed of how fast you can do an MTTV simulation and how different hardware essentially compares. So this is the basic update equation. So the field at a given grid point and at a given time can be computed using the field at the previous time step, plus, and see there are some conditions that we can assume are just constants, plus essentially some factor that includes that prefactors the curl of the H field around the nuclei. So to run your simulation, we have to update each of the E and H field components at every grid step and for all the time steps that you need to run. Right? So how fast you can do this individual update basically tells you how fast you can do your whole simulation. You just multiply times the number of time steps, number of grid points, and 6 field components. So it's enough to basically just analyze this one equation here. And what will be important when thinking about what hardware can this run on well would be basically counting the operations that you need to do. And the operations that you need to do include loading 5 fields from memory, so the field at the previous time step plus the 4 adjacent fields. Then performing 6 floating point operations, so these are just mathematical compute operations. If you count all the multiplications and additions, they add up to 6. And then finally, you have to write 1 field to memory, so that's your updated field. So that's the 6 memory access operations and 6 floating point operations. So now that we've kind of established this, we can turn our attention to a simplified and kind of a picture that tries to generalize what a hardware, what a processor really is, and to kind of just, again, very simplified. I apologize for people who are experts on these things, but the point here is really to get some basic understanding of what's happening. And so any processing unit would in principle have these 2 main capabilities: shuttling data in and out of some sort of device memory, and performing mathematical operations which happen locally inside compute cores once the data is there, right? You have to load the data on the compute cores, do some operation, and then probably write them something like that. So the main difference between CPU and GPU then can be understood by looking at both the cores and the memory bandwidth to the external memory. And so CPUs generally have a smallish number of cores. They're general and powerful and flexible, most precisely, in the sense that in CPUs, compute cores can execute completely different operations, completely different logic independently. So we can parallelize heterogeneous processes on the different cores, and they will work fast and fine. Like they will utilize the core fully. There's relatively low memory bandwidth compared to GPUs because there's fewer cores. There doesn't need to be usually that much input-output happening. GPUs, on the other hand, have many more cores, usually like 2 orders of magnitude more cores than CPUs. Those cores are, first of all, a little bit slower usually, so there are many more. They're usually a bit slower in terms of just operation frequency, but more importantly, they're more restricted in what they can do. And specifically, to be able to fully utilize the cores of a GPU, all of the, maybe not all of the cores, but like the cores come in kind of bundles, and all of the cores in a single bundle have to be running the same instruction, just with different data. So it has to be, so if you have a for loop that's kind of trivially parallelizable, so all of the whole instruction in the for loop is the same instruction that every core has to run, right? Just operating on different chunks of data. If you have some heterogeneous instruction where one core is supposed to do something and the other core is supposed to do something else, that's not going to work on a GPU. So that's kind of what, so the GPU cores are meant to speed up these types of operations that can be framed as many individual processes operating the same instructions on different bits of data. So, you know, the reason why it's so popular with AI, for example, is that matrix multiplication can be framed exactly as something. So you can speed up matrix multiplication a lot. Because of all these cores, you have to be able to feed them data in and out, and so typically GPUs also have a much larger memory bandwidth. So they have a lot more cores and a lot of memory bandwidth. Now, the memory bandwidth, unfortunately, is not 100 times larger than on CPUs. It's usually more like 10 times larger, but that's still quite significant. All right, so with all that preparation, we can, what I'm plotting here is, again, trying to understand a general picture of, if you give me a default hardware, maybe I can look at the like specs sheet, like how fast should I expect that my simulation will be? And based on what we established here, that you need 6 memory operations and 6 floating point operations, you can basically make a very simple model given the memory bandwidth of a particular chip to its device memory, and given the maximum throughput of floating point operations that the cores that are available can do, assuming that they can work close to 100%, that they're well utilized. You can make a simple model about what your expected speed of the simulation would be. So that's what the background color is showing. And this is just in units of a billion cell updates per second for these particular figures of now, the important thing to also point out is this black line here. Now, this black line here separates two regions. The region above this black line, your speed is limited by the bandwidth of the memory access to your device memory. That means that you're basically not utilizing your cores well enough because they have to wait for data to be loaded and then written back. The region underneath this black line is the opposite. Memory bandwidth is sufficiently fast to feed your cores, and your cores are working hard, and you're just limited by the fact that if you could add more cores or if you could operate them at a high frequency, you would be getting faster. But importantly, in this region here, it's the opposite. Like, you're basically not utilizing all your cores. Even if you add more cores, your simulation is not gonna run faster. It's just going to be bottlenecked by the bandwidth. And so now that we established that, you also see that I have put some common CPUs. This is like some common high-end desktop CPUs. These are some HPC CPUs. Here, this is like more like a personal GPU, and these two are more like data center, like the high-end GPUs. And two things, or several things, I guess, can be seen immediately. First of all commercial hardware is pretty much bandwidth limited for this particular application. You're way above this line. And now this observation is usually true for sparse kind of simulations so if you're doing some physics where fundamentally you're doing so FDTD can be thought of as a sparse matrix times vector product. Your system matrix is sparse, and you can put all your fields in a vector, and each time step is essentially multiplying that sparse matrix times that updated vector. So usually for such type of sparse physics, which often happens in physics, you're going to be bandwidth. Now if you're doing dense, so a lot of AI is actually compute limited because there you have dense matrix multiplication. In physics too, obviously you have dense methods as well. There it might be the opposite, but in this particular case, so I mentioned that we have 6 reads and writes and 6 floating point operations. Usually a rule of thumb for GPUs, for example, is more like you need, so we have like a 1-to-1 ratio. You actually need this to be at least 1-to-10 or 1-to-20 or something like that to really get into the region where you're utilizing your cores sufficiently. So for every memory operation, you need at least 10 or 20 floating point operations, which is not what we have. So we're bandwidth limited, but the second observation is that GPUs are still way better than CPUs because of the larger bandwidth. And now finally, if you want to push this kind of line of reasoning a little bit, what would be an ideal device? An ideal device would be a device that doesn't need to read or write to global memory at all. If you could arrange your cores in a way that matches your simulation lattice, for example, and only local communication is needed. Now, all modern hardware, and this is what this node is saying here, generally has levels of memory, actually. There's a hierarchy of memory. So here I'm really talking about the memory to the outside-most global memory. But there would be like an L2 cache, an L1 cache. In CPUs, there's multiple levels. And if you can only go through the local memory, this bandwidth is like exponentially faster as you go deeper in. So if you don't need to communicate to global memory, if you only communicate with cores that are nearby, technically, like this can actually be much more faster. And in some sense, the ways to improve the FTP speed beyond what this model predicts is exactly to try to utilize caching as much as possible. And that's getting into more advanced topics that I'm not going to. So this, everything I showed you so far, or most of the things I showed you so far, recently appeared in an article in Optics and Photonics News. We rolled this together with some people at NVIDIA. They provided these graphs also about how memory bandwidth has been increasing in GPUs in the last decades. It's an exponential increase, and that's also partly what is making things better and better for us. We go faster and faster. We wish that the exponent could be larger, because it's not a very large exponent, but it's exponential. Specifically, the compute speed is increasing faster than so the exponent of the compute speed of the cores is bigger than the exponent of the memory bandwidth. It's harder to increase the bandwidth. But it's happening, and so the memory bandwidth of an individual GPU basically tells you how fast you can do a simulation on a single GPU. The second important figure of merit for us is also how fast can individual GPUs communicate. And this is the second plot, which shows exactly the bidirectional bandwidth between GPUs that can be achieved with modern hardware. So NVIDIA is developing not only the GPUs, but also something called NVLink, for example, which is currently the fastest way for individual chips to communicate with each other. It's tailor-made for connecting GPUs in a fast way, high bandwidth between the connections. Now, how fast you can connect GPUs together tells you, given a single simulation, how fast, what's the absolute fastest I could possibly run it. Because if you start throwing more and more GPUs, and your connection between GPUs is not fast enough, you're going to get bottlenecked. And at some point, your time will start increasing because you're bottlenecked by the interconnect speed. So both of those things are important, and essentially the fact that the interconnect speed has also increased a lot allows us to really push the simulation time or the simulation speed to levels that are not just the single GPU level, but to levels of spreading out the simulation over multiple GPUs, having them work together, and having everything be super fast. So I'm going to get just to a couple of examples to showcase some of the things you can simulate and the scale that you can simulate. Because essentially, also another point to drive home is that speed enables scale. So if you're used to, let's say, if you want to limit yourself to doing simulations within a few hours for each simulation, then okay, if you're 100 times faster, now you can do them within minutes. That's great. But that also means that the simulations that you can do within a few hours are 100 times bigger than what you used to be able to. And that's maybe even more important, because basically what this enables is doing first principle simulations of devices that previously had to be done only with approximate methods. So you could never be kind of sure whether this works or not. So here is an example of a device that was, we don't have anything to do with this paper, we just replicated the device. Here it was designed with an approximate method. We did it using this first principle FTD simulation. This is a lithium niobate waveguide coupler. And this picture is a bit misleading because it's just squashed for visualization purpose, but these are regular waveguides that have thickness of the order of a micron, and the whole length of the system is 2 millimeters. So actually, this side is 2,000 times larger than the waveguide for the simulator. So for people who have any experience with simulations like that, they should know that doing this in FTD is crazy large. And we could do this in 15 minutes per simulation. So we have T and T. And I think this utilizes 32 of the A100 GPUs working together. And yeah, I mean, if you have to do this on a desktop CPU, I think this is pushing to the point where it's just impossible. Right? We're talking about 2 weeks or something. I don't know. Like if you have a good desktop and you try to run convention.
We used to compute like for 1 week at some point. Right?
Yes, that's true. Yeah. And that was not nearly as big. It just needed a lot of timestamps. Yeah. And another example for people maybe who do meta-analysis or interested in meta-analysis. So here we could do 1,000 meta-atoms diameter. So this has close to 1 million meta-atoms. And this actually took even less time than the previous example. It's bigger spatially, but it requires fewer timestamps, many fewer timestamps. Because we also have GPU-accelerated field projections. So you only need to compute the field through a thin slice of the meta lens, and then you can take the fields and use the Green's function projection to, because after that you're just propagating to free space, to the focal plane, and so we have also a GPU accelerated version of that. So you don't need to do the simulation of the geometry to free space. So this was even faster, and again, this is something that previously people would not even consider trying immediately. This is something that you would only do with approximate methods, some local periodic approximation or something like that, and you don't know where what you do. So. Okay, I'm gonna have a sip of water. Maybe since I'm switching gears quite strongly in my next section, I'm gonna ask for a quick round of questions if anybody wants to bring something up already.
So I don't understood well if it's problem dependent. Basically, so if I deal with the sparse matrices, I'm more or less more memory bounded, right?
Usually, of course, it will depend on.
So I have to search with a computer that has a larger memory bandwidth, in some sense. Okay.
Now it also really depends whether your algorithm parallelizes well. So, for example, if you, I don't know, if you're doing eigenmode solve, that's much harder to parallelize than just repeated matrix multiplication. That's very easy. So, if you're doing eigenmode solve, and you have sparse matrices, then your problem might be not so much bandwidth as this problem that you need all cores to be doing the same, if you're trying to put it on GPU, that you need all cores to be running the same instruction, and that's, depending on the numerical method you're using, that might not be the case. You might be able to frame it like that.
So I think this question is very important. So if I have a problem like time evolution, not of actual equations but of our equations, which amounts to the same sparse time spectrum.
Yep.
Okay. So now I have some platform that tells me I'm GPU ready, so you just change one line of code and it runs on GPU. Am I doing something which is clumsy in general if I do that? Or and is there a general criterion that I can adopt beyond the photonics and beyond your specific products to have the same insight into what I'm doing and possibly improve?
Yeah.
I mean, what would be your
that's a great question. I would say that actually probably getting to the level of having this speed model, so achieving the speed that this model would predict by just using some high-level platform that allows to convert your code to GPU, that's probably going to work. If your code is as simple as like sparse matrix multiplication or something like that, that's probably going to work. If you want to push further, either because there's other operations, so in our particular case, like I said, it was the absolute most basic FTPD update. But once you think about boundary conditions, dispersive materials, monitors, recording fields in the simulation, all those are different operations that you might have to think about sometimes on the lower level. And also if you want to go potentially to the point of utilizing the cache of the computer better, that might require some more manual tinkering. So basically going beyond this model probably requires that, going lower level in coding as well. But achieving the speed predicted by the model is probably going to be straightforward even with the high level software.
Sorry, let me say this for the sake of everyone. I mean, we were discussing a lot, is there going to be a link to quantum in your talk? Here it is. It is very fashionable today and very important to simulate accurately superconducting devices. In particular, there is all this series of people who are simulating readout process and gates and so on. And these are systems that if you quantize, and they don't do, they are, so the rotating wave approximation doesn't work. Mm-hmm. This means that ideally you have to simulate over a very, very tiny time step in order to account for the rotating, for the main figures, okay? Perhaps this is a stupid approach and there are some tricks out of there, but apart from that, the task is the same, is multiplying some sparse matrix, which is the Hamiltonian and the dissipators times your density matrix. And having ideas of this kind may have a huge impact in this field because these people are trying to optimize quadrants. There are papers out there who are very, very sophisticated in terms of optimization, but perhaps not as much in terms of the basic single instance simulation.
Yeah, just get a single simulation fast and then you can do a lot.
Yeah, so that's exactly where it connects. It connects in exactly this, I think.
A very simple question. So I assume that for FTP, for finding the fields at time t, you need all the fields at time t minus 1.
Yeah.
So in fact, the parallelization cannot be done in time. Rather, it's done in computation. All of these multiplication and stuff. I mean,
Yeah, you iterate over your grid points, over your spatial grid, right?
Yes. So all of this parallelization is done at the computation of these multiplications, the summation in space, not in time.
In space, yeah.
Okay.
Okay, so yeah, so like I said, this kind of goes into a very different topic, and I'm going to start a bit with the basics, and I'm going to try to explain to you what the automatic differentiation means, roughly. Again, for people who are experts, maybe they will don't judge me too much, but I have limited amount of time. All right, and now we're really stepping way back, and we're just going to think abstractly about what does a program do usually? What does when you write some code, what can we think about it on the conceptual level? And on the conceptual level, basically, you are probably using some library of functions, which maybe are existing, somebody has written for you, or maybe it's functions that you have written yourself. But in any way, you just have to build a bunch of atomic building blocks that take some input and produce some output. This is extremely as generic as it gets. And then your program is just some sort of computational graph where you might have some inputs, or you always have some inputs and some outputs. And in the middle, you might have multiple inputs. You might have some of the inputs of some of the outputs of some of the building blocks, or inputs of other building blocks, and so on. But very conceptually, a program is just some sort of computational graph that gets evaluated by progressively applying functions to transformations, to inputs to produce outputs, and combining potentially and so on. All right. So this is usual programming. And then automatic differentiation also has another name, which is differentiable programming. And it just extends this conceptually to add, let's say, two crucial extra parts to these basic building blocks. First of all, each of your atomic operation needs to be defined in a way that not only knows how to connect inputs to outputs, but also knows how to compute the derivative of the gradient, the Jacobian in general, with the x and y vectors, of the outputs with respect to the inputs. So let's say this function is sine of x, then your library should know not only that it needs to do sine of x when it gets an input x, it should also know that it needs to do cosine of x to get the derivative. And the second important thing that the differential programming library will do is it knows how to not only evaluate such a computational graph, which is what, like I said, just running your program means, but also how to use the derivative rules, specifically the chain rule and the sum and multiply rules, to not only be able to do the forward iteration, but also to compute, to change the gradients in a way that you can in the end get the gradient, let's say, of x6 with respect to x1. This is, again, very roughly what automatic differentiation refers to. And maybe an example would illustrate better for people who will calculate this for the first time. So if you've used Python for anything numerical, you've certainly used NumPy. It's basically the way to do math in Python. And one example of a AE package is called AutoGrad. It's very lightweight but very powerful. And essentially what it allows you to do, so it kind of does, it converts this of regular NumPy into this of a NumPy with automatic differentiations. So instead of importing a regular NumPy, you can import AutoGrad of NumPy as the way you usually create NumPy. And now you basically can write functions that you can just take the gradient of, like apparently for free. You don't need to do anything special. So we can define a function here where, for example, we take the sine of x and we square it. Then we can test it on some initial x. So this calling the grad on the function just produces another function which returns the gradient. And then when we evaluate the g of x, we get exactly what the analytic gradient would prescribe. And this is because basically, like I said, AutoGrad does this. Like it knows for sine of x that it needs to do cosine of x. It knows for x, for the square, that it needs to do twice the input, and then it also knows how to combine everything to produce the answer. So this is not symbolic differentiation. It's not what happens when you ask Mathematica for the derivative of an analytical expression. And it's not numerical differentiation either. So you will not put, it's really like this idea of having the atomic blocks that know how to do derivatives of the elementary operations, plus a way to track derivatives through the computational graph. So, and I would say that basically any machine learning package at its core, and very minimally, but mandatory, is a automatic differentiation package. So if you take something like PyTorch or TensorFlow or JAX, one of the fundamental function of these packages, one of the fundamental functions, is allowing you to write very complicated computational graphs, which your learning models usually would have, and being able to compute the gradient of your outputs with respect to nowadays billions or hundreds of billions of parameters that you have in your matrices. So all this needs to happen automatically. You only say, all right, take my inputs, multiply them by matrix, apply some nonlinear function, repeat that, branch off, whatever. You only define your computational graph, or in some sense your program, how you evaluate the connection from inputs to outputs. And what these packages essentially provide is that you just compute the gradient easily and efficiently. And I cannot stress this enough how much this underpins machine learning, because it basically allows you to train these models. Like, there's no other way to optimize billions of parameters than through some sort of gradient approach currently. People are working on it, on alternative ways, but it's like practically everything is always going to be gradient optimized for getting that scale. And then to do this efficiently also brings me to another fundamental concept in automatic differentiation, and that's the difference between forward mode and reverse mode. And this is, in some sense, a super simple observation, an idea, and in another sense, extremely impressive and familiar. And to illustrate it, I'm just going to consider like a super simple computational graph where you just have three operations in sequence. All right, and then your chain rule is your gradient of the output with respect to input, which is the chain rule of these Jacobians. So let's assume that, like I said, these are Jacobian matrices, these are vectors. So each has some dimension, n1, n2, n3, n4. So the whole point about the difference between forward and reverse mode AD is that when you're doing matrix multiplication, so if I just give you three matrices and I ask you to multiply them, how computationally intensive that would be would actually matter on how you choose to compose the multiplication. Whether you do this side first and then you multiply it and this, or you do this side first and then you multiply it like this, actually matters. So it's not commutative in that sense. And more precisely, if we put the brackets here, so if we do what's called forward mode accumulation of the gradient, and it's called forward mode because we first multiply this one by this one, and then multiply this one by this one. So we follow the exact same trajectory that the initial computation follows. So you can think of the computational complexity. Here I'm just assuming that multiplying matrices of this complexity. You can do better than that, but I'm not going to go into that. And you can think about this for a little bit, and you will see that the complexity of doing the operation this way is really important. If you do the opposite way, if you first do this multiplication, which means going backwards in the computational graph. So it means multiply this by this, and then multiply the product by this. So that's why it's reverse mode. Then the complexity is different. And one thing that actually happens, and that is universal, even if you have much more complicated graphs, is that here in the forward mode, the n1 is always scaled. So all of your complexities will be proportional to n1 times something else. In the reverse mode, the n4, so the last size of the output is always scaled. So all of your complexities will be proportional to n4, the size of the output. And now this turns out to be really, really crucial because in typical situations when you have some optimization problem, and like your final output is just a single element. You have a single scalar that you're trying to optimize. So n4 is 1. And in many cases, n1 can be millions or even billions. So the difference between these two complexities becomes immense. And reverse mode automatic differentiation is also called backpropagation. That might be a term that's more familiar to people. And it's again pretty much what has enabled deep learning. Like we cannot do these models without backpropagation. Yeah. And the super interesting thing about this is that you can compute the gradient of some function with respect to, like I said, let's say billions of parameters with about the same computational complexity typically as just the forward iteration of the forward evaluation. Now, there's a caveat here. Reverse mode AD is more memory intensive. So in some cases, you might start running into problems with memory. And that is because when you go backwards in your graph, it means that you have to save all the intermediate values. So that's a caveat that needs to be taken into account sometimes. But in terms of computational time, reverse mode AD is extremely efficient. All right. Maybe I'll again see if there's a question here, because I keep oscillating between various topics, so maybe better to answer questions right away.
As you know, at 1:15 we teach introspective, so at some point we can see the thing, but I would like to see our stuff.
Yes, this is our most highly cited paper from my time in Vincenzo's group. It is about, so this was the automated optimization of the photonic crystal slab cavities. That was one of the cavities that we optimized. So now this is again a little bit unrelated to what I just showed, but I'll get to the connection. Because here we did not use any of this automatic differentiation. Here what we did was we had a very fast way to simulate a single device like that. We took only a few parameters and we asked the computer to, we used a genetic algorithm specifically, to just find the best device. And previously nobody had done that because simulating a single device would take hours or more. And I think this improvement to 5 million was more than an order of magnitude higher than the previously published designs for the same essentially resonator. It's three missing holes in a wall here, but nobody had done like a good optimization. And part of the so like I said, the fundamental reason we could do that was because we developed a tool to simulate these things that was very specified to simulating photonic crystal slabs, but very efficient at doing that. So we would do a single simulation in a few minutes, and once you do that, you can plug it. You can just use a regular optimizer that comes off the bat from SciPy or MATLAB. If you have a fast way to compute your function, and you can do 1,000 iterations overnight, you will already most likely get really good results if you only have a few parameters. Now, the relation to automatic differentiation is, so I'm not going to explain how the method works, but I'm just going to say this is like a high-level view of the computational graph of the organic multidimensional. And there were some complicated operations in there that include Fourier transform, matrix inversion, some eigensolves, also some nonlinear solve to find the guided modes of the slab. And then here you get the real part of the frequency of the eigenmodes, and then there's finally like a radiative overlap step that you do together, so the imaginary variance, so quantify. So then actually one of the last things I did at Stanford was to take this code, which was initially in MATLAB, and basically write it from scratch in Python using AutoGraph. And what that means is that, suddenly I had this code that could do the simulation fast and was also differentiable. So I could compute the gradient of the quality factor now with respect to not just a few parameters like we did, but with respect to, let's say, the positions of all of the holes. Basically the time to compute the gradient with respect to one hole or with respect to all of the holes is the same. Because of how efficient this reverse mode AD works, it doesn't really matter. It's about twice the time it takes to do a single simulation, and you get the gradient with respect to all of your parameters in one shot, which is like really amazing and often feels like black magic to me, but still haven't gotten used to how amazing it is. Now I did have to do some So the computational graph, like I said, it's very complicated. Like each of those blocks, it's a high-level block that actually has a lot of code in it. But if you use the autograph NumPy, it's handled. The tracking is handled automatically. And one thing that I did have to do is I did have to implement some custom backpropagation rules, because, for example, the matrix eigensolve was not something that's supported by NumPy autograph. So there wasn't like an autograph eigens function that had knowledge about how to do derivative to that. And by the way, to add this knowledge of how to do derivative, it's basically it can be derived. One way to derive it and to understand it is through perturbation theory in quantum mechanics. So what is to define a derivative of an eigenvalue of a matrix, and perturbation theory at the limit of a small perturbation is exactly what it is. And all that is in. So yeah, this paper actually has quite a lot of discussion on introducing automatic differentiation to the more EM simulation community, which wasn't really probably aware of that. So there's a lot of background on the data as well. And here, for this cavity, which is not the same as the previous I showed, this is a slightly different cavity model, but yeah, so the Q actually could optimize it in several orders of magnitude, and this cavity has a small amount of okay, this now takes me to a related part of my talk about inverse design and the adjoint variable method in particular. And I would say this is already an example of inverse design. When people, or even this is an example of inverse design. So inverse design is a bit vaguely defined, but roughly speaking, you have some target, like it's an optimization problem. You know what your device wants to do. You maybe have a device that can kind of do it, but not very well. How do you optimize? How do you get a device that can do it really well? That's kind of what people mean when they talk about it. And in many cases, and this is a figure from a review paper that I always show. People are interested to know more about this. In many cases, inverse design comes coupled with something that's called the adjoint variable method. So especially whenever you see these types of kind of what we call topology optimized or freeform optimized structures, where you really have some really non-trivial structure happening here. In many cases like that, the underpinning kind of last bit of the puzzle is called the adjoint variable method. And I'm quickly going to explain that as well. And to understand the adjoint variable method, again on the very fundamental level, it's important to think about conceptually what does solving Maxwell's equations, or in principle actually many other simulations, what does it mean to solve, and specifically in this case I'm going to think about the frequency domain. Because almost everything we do in these devices, we care about the frequency domain, we care about the spectral response, we care about usually some sort of scattering matrix or some sort of spectral response. So solving Maxwell's equations in frequency domain is basically a linear system. So in time domain, we were iterating this matrix. This matrix A here is going to be almost the same matrix we do in time domain. In frequency domain, it's just solving a linear system. So the formal solution is this. So the electric field inside your simulation, given some source B and some system matrix A, is given by the linear solve of the system. And the adjoint variable method is basically the prescription about how to do backprop through that linear solve. Of course, we don't actually invert the matrix. Usually, we just do the linear solve. But the question is, take this as one of the building blocks of your program, right? How do you do the derivative? How do you do the backward step? Your input is your system matrix, which contains the, let's say, permittivity of the materials, and your output is your fields. And how do I backprop through that? And I don't have time to really go into the mathematics, but the interesting thing about it is that if you do go through the mathematics, it actually even looks like backpropagation physically. So not just in a computational graph kind of sense. But to illustrate this, if we, for example, take the example of having a source at a given point and a monitor at another point, and we look at the output as the field at that point. So let's say we try to maximize transmission from this point to that point. it turns out that the gradient of that particular output with respect to the inputs, which are the material properties in the entire simulation, so the permittivity everywhere, can be computed using just two full field simulations, so the forward and the backward one. And the forward simulation is just your starting one with the source in the starting point. The backward simulation, the monitors become sources. So the backward simulation really is injecting at the point that you were recording at previously, so it really looks kind of like backward relation. And then the gradient everywhere is just an interference term between these two fields. So this profile here, after doing these two simulations, tells you at every point in your simulation, depending on whether this is positive or negative, if I increase the permittivity there, am I going to get higher transmission from this point to this point, or am I going to get lower transmission from this point to this point? So if that's your objective function, you can now start tuning your whole system simultaneously at every step to maximize that, or to minimize that, or whatever it is. So given that part, are we now ready to take a device and just tune our permittivity as we want and to get our optimization step? Well, almost, but not exactly, because the adjoint variable method itself just gives you the prescription of how to do gradients of fields with respect to permittivity. Normally, what you would have is a more complicated computational graph if you really want to do a device that works in practice, or if you care about some complicated final parameters and so on. You wouldn't be looking at transmission to a single point, for example. So you might have some complicated post-processing where maybe you care about some motor overlaps, maybe you care about multiple frequencies and so on. So you would have some part of the computational graph that will be doing some complicated combination of things usually. And you'll probably have some complicated pre-processing which takes some parameters, maybe applies some fabrication constraints, maybe applies some custom shape parameterization, or something that converts your raw parameters into a permittivity profile. And the adjoint variable method is essentially the part about how do you backpropagate through this part. But to really be able to do optimizations, you want to chain everything into some sort of AD kind of thing where you can backprop to everything. And this finally brings me to input design for everyone, because that's kind of what we have done in Digest3D. So we have a plugin that combines our speed advantage of doing the individual simulations with a very convenient way for people to convert any simulation into an optimization. So you would typically have, like I said, if you're optimizing a device, you would have such a complicated computational graph. But because everything is linked, you only need to define your forward simulation, and then backpropagation is handled automatically. We actually have both the jacks and autogate. We also have some predefined things to simplify life. So probably the single most crucial element about photonic inverse design to really make it a thing that's used in industry, let's say, and something that's really used in practice, is ensuring that what you design in the end is fabricable and fabrication tolerant. So if you have small errors in your fabrication, or it doesn't come out exactly as you and anybody who's done fabrication knows that this will always be the case. Ensuring that it's fabricable is probably the most important aspect of this. And it's still not a solved problem, honestly, but we have like some predefined fabrication constraints and penalties that can help you do that. And then in the end, once you define the state, you have an efficient way to compute gradients of your objective function. You can take these gradients and plug them into whatever optimizer you want. Like, we don't do that much part of the how you optimize, because you can just use completely separate black box optimizers once you have the efficient simulation and gradient computation. And how it works in practice, very high level, but so you would usually have, so we have both the Python interface and the graphical user interface. I'll show a little bit of the graphical user interface in the end. But in the Python interface, you will normally have some function that creates a simulation if you're studying something. And so the only thing I'm showing here is how you convert, or what I'm showing is that there's really minimal effort to convert a simulation to an optimization, or to a gradient computation. So usually you will make the simulation. One thing I didn't say is that our service runs on our cloud. So the way we provide the hardware acceleration, the way the simulations run really fast for users, is you just need your laptop and an internet connection, and we do the hardware allocation for you. When you do this web.run, the simulation gets sent to our servers, and a big simulation will get assigned to a lot of GPUs, a small simulation will get assigned to not a lot of GPUs, but everything will run fast. And in the end, yeah, basically, you get the data returned, so you download the data back. And then finally, you will have some figure of merit based on your data. And like I said, we've written everything in a way that you can then just call this autograph grad function and also compute gradients of your function inputs with respect to your final figure of merit. Now, under the hood, it's actually quite complicated. This web run through the cloud adds an extra level of complexity of having everything chained together in this computational graph. And these are just some images from our internal kind of discussion of how everything pieces together. But we've done the hard work for you, and like a user doesn't need to know what AD means or what agent diagram means. And finally, I'm just going to flash a few examples of things that you can find among our online examples. They're all in the form of Python notebooks. So, and also, by the way, anybody can register for a free account that has some credits, simulation credits on it, and you can request an educational user account, which even gives you free credits every month. So, all these examples are in the form of Python notebooks. So once you have an account, you can actually run them for yourself or modify as you want. So this is a waveguide demultiplexer. Each wavelength of the input needs to be directed to 4 different channels. So this is just an example that we can do complex broadband objectives. This bi-level grating coupler where 2 design regions are co-optimized. So one is silicon, one is silicon nitride. This is a metallic antenna where, so just to illustrate, we also support dispersive media in the optimization. And then this is a shape optimization, which I actually quite like, sometimes better than these kind of very free-form optimizations, because this is really hard to convince someone to try to fabricate, because they're not going to get it out. Or it's going to be a lot of effort to get out of your fab. I mean, okay, if you're doing e-beam lithography, you can do it. But if you want to mass produce this, like using, just going to some foundry or something and asking them to do this for you, they would like it. Here, this is moving boundaries essentially, where you parameterize the shape of your component, kind of the outside shape, and you can still apply some penalties to make sure that this is fabricable, so that features are smooth enough. And this could be much more easy to combine with whatever constraints you have in fabricability, and you can do that as well. And then also, just apart from things like so outputs like mode amplitudes or diffraction mode amplitudes are differentiable, and even just the raw near and even the far field amplitudes are also differentiable. So you can write your figure of merit as a function of, let's say, your far field radiation, and even that is backpropped to correctly. So here, you do the simulation, you put a near to far field projection monitor on top. The figure of merit here was to separate the 2 incoming polarizations into 2 different angles, and you can do that. Oh, and then, yeah, I'll just, very soon we'll have a GUI version of this simulation as well, so you don't need to do it, right? This is a quick example of also how, what a GUI looks like for regular simulations and for optimization. It's all sound here, so I'm just going to narrate. So what's happening here first is, so simulation was already defined with 2 waveguides in and out, and like a middle region that's initialized to just be like a constant material region. And so this is just a starting simulation, which doesn't show much, but the goal is, this is what happens, this is what your starting device is. But the goal is going to be to make a pen and to make this light coming from here to go down here. And we're going to do this using this topology optimization. Freeform. So you can convert this simulation, this typing simulation, to a topology optimization, so inverse design optimization, where we need to set a few things. specifically set the design region within which we want to optimize. So we're going to say in here, we're going to, this is going to be our few parameters. We need to define some metric, and here is just going to be the amplitude of the intensity of the light coming through the bottom right guide. That's going to be a metric. And then finally, we need to set the optimizer. We're going to run it for 25 steps, and just with the learning rate as well. You always have to validate before you run the simulation, but then after that, in this case, optimization. And now the optimization runs in the cloud. And you can monitor as the steps here above are progressing. You can monitor both how the field is starting to get towards where you want it to be, it's starting to go down. And you can monitor how the material distribution evolves. And you can also monitor the objective function. So here we have objective function and a penalty term for the smoothness of the feature. And you can also, so you can see what you got, and you can finally even export this to a GDS. And I believe that's it. And I hope I've conveyed the message that the recent software and hardware advances have really opened up a lot of interesting things in doing large-scale simulations and also doing more and more complicated and interesting things. And that really opens up people's design to users even if you have no prior experience. Just convert your simulation from optimization, and I think that makes the future of large-scale optimizations quite exciting. And here are some links, and like I said, flexcompute.com also will have a lot more as well, and you can find everything there, including how to make an account and just start trying for yourself, in case you're interested.
My name is Rafael Piquet. I'm a senior scientist at LASP, one of the laboratories of the Institute of Physics, and because Vincenzo had to leave, he asked me to moderate the questions you want to ask to Momchil. So, yes.
Thank you very much for the talk. I have a very general question. So, at the end of the day, what you're doing is that you are solving a PDE with some given boundary condition and initial condition. So now, if we have the PDE, our own PDE, can they give it to you and you solve it for us?
Probably not. Because unless you're willing to pay us a lot of money for it, because it's still going to be some work, right? Like it's not. Every PDE will have a different considerations to it, but we are expanding into other solvers, like I was saying. So we have fluid dynamics. But yeah, at the end of the day, to make it usable as a product by someone who really made by industry people or by people who don't have a lot of time to do a lot of the work on their own, you need to add so many just conveniences and features and things like that. If it's a matter of simply taking like a very fundamental PDE and making it run on a GPU, it's not so hard. But okay, it's not something that we would do. But I think the main, basically having a GPU FTTD takes a week. Having a GPU FTTD that people want to buy takes 2 years because of all the conveniences that you need to implement along the way.
Yes.
Can your TEDdy 3D use it for solving something like our superconducting devices, solving the eigenmode of the electromagnetic field, or solving the input and output spectrum, something like this?
So we are working on, mostly we have focused on photonics so far. We are working on expanding into RF frequencies. The crucial bit there is, often you would use a finite element solver, an unstructured solver. You can do a lot with FTTD as well. So we're probably going to do both eventually. For now, we're working on expanding TEDdy into the RF domain. The main, there are a lot of details there. The main thing is the fact that you have this Cartesian grid, and the fact that you have these metals where you have extremely strongly sub-wavelength concentration of fields is generally quite problematic. It means you have to either mesh very finely in some regions, but then you still have like a giant simulation. And there are ways around that, both in terms of smarter meshing and in terms of methods to do subcell smoothing of, let's say, conductors. And we're working on all that. So eventually it will be like, I guess, similar to if you use CST for something like that, and specifically the finite difference CST. If you haven't, we're working on it. Thanks.
Other questions? Yes.
First of all, thank you all for doing this talk. I have, let's say, quite a general question regarding the amount of time that's needed to do the inverse design of, I don't know, a couplet. Like, I was designing basically a photonic coupler for TMDs, so two-dimensional materials, quite, let's say, unrelated but related at the same time because it's optics. And I basically found this paper where they were doing this kind of coupler, and the time needed to optimize the inversion was around 27 days. So what about like the time that instead is needed using 33D for doing this kind of?
Well, so that's why the hardware acceleration is a crucial component of it as well. Yeah. So
like, let's talk about time. How much time is for the instance like that?
Well, so it really depends on your simulation, right? But so, for example, the simulation that you ran, that you said 20-something days, was that on just on a desktop computer or something like that, or?
Yeah.
So typically our speedups with respect to just a good desktop computer are like maybe about 2 orders of magnitude. So that would already put you would probably put you in the hours, or maybe worst case scenario like a day kind of thing rather than a month.
Yeah, and then what about like the number of parameters that I need to optimize for, and like for the inversion, in order to go like that to the design? Of course, it really depends on the number of parameters I would like to optimize. So is there like a limit that already like imposed, or?
So yeah, it's, let's say on a fundamental level, I was trying to explain that the reverse mode differentiation actually gives you the gradient roughly independently of the number of parameters. So whether you're computing the gradient with respect to a single parameter or all of them, takes about the same time. There are problems though. One thing I mentioned is that it is more memory intensive to do it this way. So you might run into trouble like that. And also it's not truly independent when you do it in practice. So I believe we impose especially for these free-form optimizations, I believe we impose something about 1 million number of parameters that is the maximum that you can have.
Other questions? Okay. You remember that in practice when we fabricate devices, we always have fabrication intersections. So compared to the time where you did your PhD and now, how would you say we can handle this type of problems?
So one very interesting thing that we're also exploring related to that is that, and actually, okay, so traditionally the adjoint variable method has been known in engineering for maybe 60, 70 years, I'm not really sure, but at least 50 years. And especially in structural mechanical engineering. And I think long before it became an optimization tool, it was actually a sensitivity analysis tool. And so this provides you a very nice way to study those kind of things. Because computing the gradient with respect to, let's say you're doing the photonic crystal relation, right? Now you can optimize it, but let's say you already have an optimized device. You can just, computing the gradient tells you how sensitive you can expect your quality factor, let's say, to be on the, let's say, the radius of each of the holes. You might even identify a few holes that are the most crucial, right? Like those would be the ones closest to the cavity usually. But if that helps in some way, that will be great. In some cases, it cannot help you because you cannot get better than that in fabrication, but it can at least tell you very quickly what's like the variation that you can expect, what's the, yeah, it's kind of like, instead of doing, let's say, a Monte Carlo simulation where you perturb everything, you actually just know right away how much of a change in the quality factor you will get given, you know, if you approximate the things that are approximately linear, you know, you know the gradient and you have like a, you know, you have a 5 nanometer change, and you can just compute the, okay, well, approximately this is how much my figure of merit is going to be gradient. So this is like one thing for which this is also interesting, sensitive analysis. And sometimes it can actually really tell you, like if you're doing some complicated stacks, it can really actually give you some insights in which part specifically of your process needs to be optimized to get better results.
Other questions? So if not, we can thank Momchil again.